Hey everyone, welcome to another episode of the Common Lisp Study Group. I'm your host, Ron Baden with Atlanta Functional Programming. Today we're going to be continuing our discussion of Eliza, a system, as I mentioned before, that performs, well, it was one of the first systems that performed conversational dialogue with the user, and at least attempted to provide a more of a natural interface for folks who can do question answering in some way, shape, or form. We ended last week with a basic discussion of how the pattern matching approach was done in Eliza with the notion of a simple pattern matcher. And if you recall, for full details, we looked at something like this, where we had this pattern matching system with a simple equality that took pattern matching with a pattern and an input, and we simply checked to see if the pattern is a variable, and if it was a variable, it was true. Otherwise, we went ahead and went through and recursively gone through the rest of the input has to check whether or not it matches particular parts of the pattern. We also looked at the simpler version that was in the first version of Eliza, as indicated by Norvig in his repository to match what was in the book. That was a little bit more complicated, complex in that it introduced a notion of segment patterns, which we're going to be discussing today. Uh, but it is with that pattern matching algorithm and an additional data structure, which we'll be discussing today, in combination, that actually ended up creating what was eventually the rules database that was for um, Eliza to actually do conversational dialogue. Now, I'm going to mention, and the book mentions this towards the end of the chapter of chapter 5, that the code that was presented is a very simple thing. There's a lot more stuff that Eliza did do. So folks who may be thinking that this is a full version of Eliza, just it's the algorithms that actually implements what or was used to implement the basic system of Eliza, but it doesn't have things like stop words, use of synonyms, um, being able to tag uh, notions of particular types of language to indicate particular concepts, like, for example, parents or family and things like this. But the basic rules and the structure and how the for a simple version of Eliza is thought out is basically the approach that we're kind of looking into and discussing today. Before I begin on our more in depth for what we're talking about today, just as usual, for those of you who like our videos, please subscribe and hit the bell icon on YouTube. Uh, those who are in Jitsi, thanks for joining in the Jitsi live chat. We do have a Jitsi live chat for my YouTube live audience who's following along. If you want to be part of the discussion, the voice discussion, please join our meetup. We are Atlanta Functional Programming on meetup.com, and you can use that to hear more about our in-person as well as our online talks. Atlanta Functional Programming is the home of the Common Lisp Study Group. We are a group that promotes the use of functional programming and integration of functional programming patterns inside larger scale software. We are looking for speakers for those of you who have particular topics or interests in mind that who may want to present. Please reach out to me. I am Bugram on functionalprogramming.slack, as well as Tech 404, which is Atlanta's premier Slack workspace for the Atlanta tech community. And for those of you who are on Lisp who may want to present their libraries and or projects on the Common Lisp Study Group, I am also Bugram on the Lisp Discord server, which I squat on as well. And if you give me your talks, I could go ahead and schedule them accordingly. So let's begin. So let's go back to uh, our Eliza pat match function that we were seeing last week. Sorry, this one. This pattern matching function introduced something that we're going to be discussing today called segment pattern. And I thought I would point that out with an example that was actually in the book that I was kind of working through this week as I was reading this chapter to try and understand what he meant by segment variables. So the use case for segment variables is pretty simple. You might end up having, say, you see that simple example that we have there with in the REPL, where you have I need a X, where it matches the word vacation to the structure that is in I need a whatever. And what you could do is you may have different parts of a sentence that end up being in a situation where you it's different parts of the sentence that end up wanting to be matched against a particular pattern. So you want to take that structure of the sentence and break it apart into things that could be varied. All right. So like in this a vacation sort of sentence here, we could have something like along the lines of pattern match, and it is. Let me just pull this up. This is the yeah. So if we do um, let's do this one. Yeah. So we have $P need $X. And let's say that we take as input, and before I do that, because I know it's going to complain that $P is a not a function. Let's go ahead and quote that. And let's say we have the sentence, quote from the book example, I need a long vacation. Okay. And the issue with this thing that I recognized, oh right, because I'm using the simple pattern matching, not the new segmented one. The simple one, you could see that what it did was is um, it just kind of split through, and it couldn't actually go and recognize that it needed to actually go um, do additional work. So we need to go and actually extend the simple one also to handle this particular piece. So let us add, let's go back to our simple example before we get into one. Let's do slice scratch. Okay, so we need to go ahead and fix this one so we can have additional bindings. Um, let's see, we could do that with, right, we need to actually create the bindings for this. We need to create a data structure for these bindings, just like we did before. Let's go ahead and leverage. Um, yeah, I'm gonna go ahead just to simplify things for this. This stuff is already kind of created here. I'm gonna go ahead and break this apart a little bit. Go to, not that. Okay. Sorry, slide scratch. That's what I need. Okay. So we need to go ahead and do this. So we've already kind of introduced this notion of what a variable is because we have this in our sentence, but we need also two other things, which is bindings, which we actually can look at by looking at our auxiliary functions that we've seen earlier. And these bindings are basically just as you recall, the cons and the value that it founds as it goes and constructs the actual binding list. And as you see in this simple example, question mark x, the binding variable x is actually associated with vacation, the simple example. But we need to also look at no, go to hold on. Go back to my scratch buffer. Okay. We need to also actually fix this piece here to actually do something else. And so with our bindings, we can actually do um, the binding functions that we have. We can actually change it this way. We first can do let's do this. Okay. All right. So let's look at this example here. We're gonna, well, let's say another pattern match. We'll go ahead and comment this guy out. Okay, and okay, go here, define pat match pattern input, and what we'll do is we'll create a cond, and so I'm just going to show what the kind of the book did here. Like this is an example. Actually, I'm pretty sure he has this already written somewhere. Hold on a second. Let me go look at his. Eliza. Is it this one? No, no, no. This is has more rules. And go back to Eliza 1. Segment match rules. Eliza switch viewpoints. Okay. We could just do it this way. This is a very simpler one. So what we need to do is we need to first do kind of similar to what this does. This newer version has the segment variables, but we need to first look at kind of the use case as to why the segment variable is. So I'm just going to go ahead and remove the case where there are segment variables just so that you could see what the difference is. So we could just actually go ahead and copy this guy and just adjust it. Sorry. Go here. Present. I don't want to actually go in and adjust that code in there in the code there, so we can just see kind of a side by side. So we don't need this one. So we delete that, get that out of the way, and I believe this will break the other ones, right? Go pattern inputs, cons. Yeah, this is right. Okay. All right. So let's go ahead and update this. Okay. So now we try our simple one, it will still do it. But if we try this, we'll also see that it will not get. Okay. So let me try one more thing here. So it's able to get it in multiple vacations, but it can't do the I need a long vacation, which means it is dependent on so what I wanted to show you is that in the case of um, in the case of I need a so the problem is that um, it's doing an exact match here with the input, the structure. So here you can see in um, the the simple pattern match, um, it's not recognizing the rest of the input. Like if I just simply took the I need vacation and I just change it to I need a vacation, you'll see that this will also fail because the pattern matching isn't actually recursive, taking the rest of the input and just binding it. So this is not a completely huge deal. We can actually fix that by, let's see. Oh, I see. I could do it this way. My pattern needs to change to the pattern dot x. And if I made this into a dotted pair, I can actually correct this. There we go. So the reason why in this case the pattern wasn't working is because it was trying to do a single list match. So it wasn't actually, if it wasn't exactly the same, if this beginning input isn't exactly the same as this one, it will treat it as, it wouldn't be able to extract the information and then be able to bind it to the external inputs because the recursive pattern is actually looking at the rest of the input. And this goes back to what we're actually doing if you actually look at the pattern matching. The pattern matching in the recursive case, it's taking the rest of the pattern and the rest of it, which is the coulter of the actual list, since we're treating these two things as a list. So the way to actually go and grab longer inputs and writing your actual patterns, and at least with respect to this implementation of Eliza, if you want the rest of the input to be constructed or pattern match a particular way, you need to actually um, dot use a dotted pair to actually go and force the extraction to do the car and coulter of the actual list. Um, it doesn't automatically do that for you. So with that in mind, you could see that one of the issues here is okay, so we now have a pattern that actually gives us um, kind of what we want. We have the subject being extracted correctly in P, but in X, the object of the actual sentence, it's actually taking the description along with the actual object together. It's taking the rest of the input to actually go in and actually match against that bounded variable. We don't necessarily want that. So what you could do is to actually fix that is um, what Norvig does in this design, and we can also probably take a look at other ways maybe to actually go and correct this, is he no introduces this notion of a um, a segment variable. Okay, and a segment variable is nothing more than um, a variable of the form dollar, I mean, sorry, question mark star question mark X to use the clean star notation to actually indicate the segment variable. And this actually will then allow us to write a function to check to see if it is a segment variable. And you could see this simple predicate, this segment pattern.t, and I can just write it up here. It's nothing more than it's already written, but I could just show you quickly what this does. Is it basically does one thing. It checks to see if uh, the pattern that's passed in is a cons pattern. Okay, so it's a cons pair, and the pattern, okay, starts with, which he defines. Um, I think it's that, and oh, we need to actually grab start the first of the pattern starts with a question mark star like that. Okay, so that's all that is. And you can see that this segment pattern basically will just obviously for the example that I provided, it will return, oh right, because this is not a list of lists. You have to do this. Okay. Although we don't have do anything, this will check to see that it's true. And if you wrote something else, it will, if you wrote something like what we did earlier, this is going to return nil. Okay. Or if you ended up doing something like that, it's also will return nil. Okay. And this segment pattern that he created is kind of the basis for this final piece here, which what it allows you to do is it allows you to end up taking a sentence like, say, if we actually go in and use this version now of pattern match and then write, say, pat match, um, the pattern is going to be, oops, sorry, I forgot to accidentally hit enter there. And the pattern that you're trying to match is something like this, p need x, and we do I really need a vacation. You can see that it grabs the information after my typo. It grabs the information that it needs to actually go and represent the bounded variables and things. The only thing here is there's still not a complete notion here, and that is our binding notation clearly still needs some work because you need to make sure that the bound variables are named accordingly. But this can show you that you can write these structured rules, if you will, okay, to actually go in and construct canned responses based on the rules with the appropriate responses. And we're going to use these segment variables to actually go in and construct the final piece, which is um, what we saw kind of last week, but we didn't really go through it, is the uh, the rules database that Eliza was written on top of. Now, this is kind of like the rules that we saw in the case of the general problem solver, but the difference is This is leveraging a pattern matching algorithm to dispatch to a set of canned responses that can be randomly returned to the user based on what they pass in as an input. Now, given the small set of rules that this thing has, it will become abundantly clear when we start playing around with it a little bit more that some questions, the basic rules database that was provided by this simple textual example will not fly. We have to actually go in and add more rules to the database. But before we do that, I thought it would be useful to recognize the another thing that was pretty common for at least some of these systems that Norvik kind of uses almost has second nature. And as folks getting into Common Lisp, this becomes this will become second nature as well. And that is the use of lists to represent higher order data structures. So in this case, um, his rule that he created is nothing more than a list or a cons pair where the car or first of the rule is your rule pattern and the cutter or rest of the rule is your um, responses. And what's important to note is, let's go to the rule pattern here, is this is particularly useful to actually create. You create these functions that hide that effectively what your rule is going to be just a list, okay? And you write your code to actually go against this new data structure, but really it's the data structure that's aliased according to the semantics of the program that you're trying to define. And you create a couple of helper functions that you'll end up leveraging to actually go and implement your algorithm. Now, for folks who are more senior developers in other languages, this should not be news to you, right? One of the interesting things about this is this at least notation of first and rest and being able to define these functions is just fairly common that the common Lisp like optimizer actually optimizes some of this stuff out later on, especially when it compiles the code, which I found pretty neat. Um, with this construction, we can create what's called the rules database. And the rules database is literally a list of rules in that structure. As you can see here, when we're dealing with especially rules that contain um, segment variables, um, it can um, it can particularly um, be a list of lists and can get a little unwieldy in terms of potentially like say the for folks who don't like reading these number of parentheses. But this is where at least your editor becomes very useful because for folks who have these color editors like Doom Emacs especially, it can you can clearly tell both through the highlighting of where the parentheses is where the ending of the actual form ends. But additionally, the color context also helps too as well, which helps you be able to read through that code without actually doing any too much navigation. Now, before I continue on this, up until now, are there like questions about where, in, at least if in the previous episode or this episode, just what it is that Eliza does in order to implement some of this conversation? Okay. So it's fascinating just how such a simple thing became um uh was it became so useful because you could see that just by addition creating just a couple of helper functions and changing the structure of what the form is that's being passed in, you can end up doing a lot of these fairly complex things in terms of being able to uh, write out what may look like um, a simple conversation with a program, but really there's it it what looks complicated is actually fairly straightforward when you actually look at how it's implemented. One thing I do want to note is naturally for folks who may have looked at this, especially with the rules where we're dealing with something like hello and it figures out what to state. Um, it The segment variables give you the additional ability to have a flexibility as to the existence of a binding or not a binding. So these rules about like where you have Eliza blank hello whatever or blank I want X, right? Let's say that you're saying Eliza hello or Eliza X. This gives you the illusion that that you're telling Eliza what to do, but what's happening behind the scenes is these segment variables that matches it, they're throwaway variables because of the fact that they grab it and then they don't use it anymore. Because the canned responses don't necessarily need to use it. So this also gives you the ability to write more meaningful responses through the use of matching the same structure into Y. But this also, by the way, um, hits the situation where you might have, say, synonyms for the same um, pattern. Like if you say mother or father, and then you use parents or family, it gives you the program the ability to at least construct the same response that would look like if it's coming from one notion or another notion. Obviously, for some situations, this is okay. Um, but one can naturally expand this and look at this approach and see where it could break down in the cases of using a different language, for example, where the notions of gender, feminine or masculine, is required to actually conjugate a particular verb or and so on. And you need to be able to account for that inside your translation rules or your pattern matching rules. So these are some of the challenges that you'll end up encountering. But this database, as you can quickly see here, is a pretty small one. This rules database, but it accounts for some of the more basic questions that some might have. And this is what's passed in to what ultimately is something that we saw last week when we actually invoked um, Eliza, and that is, oh wait, before I do that, let's talk about um, the segment matching too as well. I forgot that we should talk about this too as well. Um, the segment matcher is a pretty interesting piece of code um, that I that we should look at, and that is given some rules like as you see here, how does the actual segment variable matcher actually go and match this information? Let's go back to what this does. Remember, in pattern matching, we're calling segment match pattern input bindings only when it is a segment pattern. Now, what it does is pretty simple. It splits the dotted pair, like you see here. Um, and it checks to see if the pattern is null. And if it is, then we're using the standard pattern of matching the variable. And the matching the variable is really just building the variable by splitting across the cutter of the segment variable, grabbing the variable itself, grabbing the input that's associating it, and associating it with a particular binding. I don't have to go through what the binding stuff is here. I think, covered it last week, but just as a review, um, if you go to auxiliary functions inside of Norvik's code here, um, there is a data structure that's really just a cons pair. We saw this earlier. Now, The more interesting piece comes into two things. One is the starting position, about when a match actually happens, and what happens if a pattern has um, two consecutive variables, because in that case you'll end up potentially getting um, a failure, a null position. Okay, so it looks for the first instance based on basic equality. We've already talked about EQ, EQL, and equal here, so I'm not going to cover that again. Um, but the additional thing here is mainly the recursive nature of this function here. So we find the position in the pattern that the first input position in the pattern that matches that variable. Okay. If it's null, that means we didn't match the pattern according to the input. So we go ahead and fail that. The failure mechanism is just a notion of there's an alias that this fail matches to. So I'm not gonna get into that. Um, but the second piece is more interesting, which is, let's say that we found something that's not null. Then what we do is we grab the subsequence of the pattern based on the position. Sorry, subsequence of the inputs based on the positions that we saw earlier, and then we pattern match that against the bindings and create the bindings here. All right. And then we do one more check to see if pattern matching against that substructure also failed. And if that failed, then what happens is we update the position to and the position is nothing more than the position the what's it the starting position that could potentially lead to a successful pattern match against the segmented variable. Okay. And this happens in a couple of cases, but this is important to understand mainly because of this situation. Like if you end up running, say, Eliza, I think one is the one that I need to use, and we end up, one second, and it's just this. Okay. If I end up just saying hello, versus Eliza hello. Oops, sorry. Keep forgetting that I can't use comma in my REPL because smart um, comma is actually a command in do me max that will, well, in Sylvester that allows me to actually go in and pass a command to Sylvester to actually go and execute, like quit Lisp or restarting the Lisp interpreter. If I say, you'll see that in both of these situations, okay, in the first one, Eliza didn't get bound to that segment variable. In the second one, it did, and yet it still ended up constructing a the same canned response. Okay. Another example of this, just to kind of drive this home, I think comes from uh, let's say, yeah, let's try that one. Let's go to the need example. Um, shift, and let's do, oh, this will be, um, oh, right. Let me quit out of this. I'm going to have to show this example because I don't think this is in the database right now, in the Eliza rules database. So let me do this here. Not pattern mock, pattern match. Okay, we do. Let me use S instead because that means subject need dot. Actually, do I need a dot here? Let's see if I can do this without it because we kind of corrected it. Need X. And let's do now Bob and I need a vacation. Okay. So in this example, you can see that what's happening in the segment variable is it's recognizing that the rule, in this case need, okay, hasn't been found yet. Okay, it hasn't found a match to that sub rule. Okay, so what it's doing is it's extending the actual phrasing so that we know where the starting position is, where the match actually can occur. And then what it does is it takes the subsequence. If it matches, it grabs a subsequence and then pattern matches that against the segment variable and then binds that into the list of bindings. So in this case, Bob and I will keep going. It'll keep eating up this sentence until it finds need. And then that subsequence, Bob and I, is then used to actually go and construct the binding for question S, and it's used later on. So this is mainly allowing the pattern matcher to actually find a point in the sentence where the pattern can successfully match, and then use that to actually go in and construct the list of bindings. And then in the case of the actual translator, it'll actually use that to create the appropriate set of canned responses. Make sense? Okay. So there's a comment about LLMs here that you're right. Like using statistical language models and natural language processing, you could actually improve a lot of this stuff and get a even better results. Although even there, I would argue that and we're going to be touching base on machine learning because machine learning is, although PAIP doesn't cover it, it's something that I have a deep interest in, and I would love to actually go through and write some more examples using it. Um, it's it's still a function of the data set, the training data set that you're going to have. Now, I will say that for folks who are using established LLMs out there, like Llama or ChatGPT or anything that incorporates the transformer architecture already with some predefined training set has a basis, you might get some really decent results very quickly for your particular use case, for especially in this case for conversation. But I would it's there is a point where it's going to start not making any sense. You just got to figure out where that is. It becomes harder and harder when you give more data to um, the uh, the training set, but there is an error there. That error is not zero. It's non-zero. It's just it's it's small enough for most. If you can make it small enough for most use cases where when it does give you a wrong answer, you know how to recognize it, then that's okay. That you will never get 100% um, uh, uh, accurate, um, uh, accurately responsive AI, especially if you're using machine learning techniques, because they are using statistics, and statistics is the goal of statistics will not give you exact answers. The goal is to give you precise answers. So that means the answer is correct within a particular error. This is something that I cannot stress enough. You, if anybody says that you're getting accurate answers with statistics, that's not true. As far as my understanding of the field and my understanding on how statistics works, you are getting precise answers. You're not getting accurate answers, and there is a difference between precision and accuracy. Um, other comments. Okay, so this is kind of what I wanted to cover, the rules database and the segment database. So now it's kind of like play time. We're going to go through some of the exercises. Um, if anybody has any questions while I'm going through some of these exercises, feel free to drop them in the chat, um, along with comments in and suggestions. And this is kind of an open discussion. So for folks who are um, have other questions unrelated to PAIP but is Common Lisp related, feel free also to drop a line and I'll try and answer them as accordingly as I see them. And let's just get right to it. So exercise number one. Um, Oh, right. Before I begin, there is one more thing. For folks who are looking at this code here, um, in uh, and one things you may have noticed in writing out stuff like this write function here, the use of pretty prints here. Um, write actually has if this is the first time you've seen pretty, I think it's important to actually explain this because some folks, I forgot that this existed in write. Um, Common Lisp has a way to actually allow you to pretty print a particular object to which a write object, I think, method override exists. So it tries to intelligently pretty print things. So if you end up saying, in this case, flattening something and then trying to pretty print it, it recognizes the underlying Lisp object that's associated and uses the appropriate writer to give you a nice displayable output. So for folks who are looking at that, thinking that this is some sort of feature that he implements, no, I think this is actually part of, if I'm not mistaken, this is actually part of the Lisp REPL. Um, and we can actually go and check that by just doing describe write common Lisp write, and you can go and look at the hyper spec for more information on this. The other thing that I forgot to mention also before we get started on the exercises is this here, this sum is important to know. If you go and look at what sum does, it's just taking a list of predicates and um, and applies it to the sequence until it figures out the existence of one such that something occurs. Sorry, it figures out the first rule that actually satisfies this particular lambda, and then it will return that rule to you. Okay. Um, Also, um, not the switch viewpoint stuff. We talked about switch viewpoint. A lot of folks who are coming in from on Lisp, all right. I know we haven't covered on Lisp on this channel, but uh, on Lisp is a pretty standard classical book that contains a bunch of helper functions. A lot of these functions on Flatten, I think Emappend, all come from also are available in on Lisp too as well. So if you guys look at that and this one, I think they will look almost exactly the same. In fact, I think since given my history of the publication, I'm pretty sure that this came out first. Yeah, this came out first before on Lisp. So um, I think some of the helper functions that he references comes directly from this book. So these are some of the interesting things I saw in this code as I was going through it. All right, so let me pull up my Scratch buffer and let us do something else. Let us go and let's save this guy to chapter 5. So this way I have my list of stuff. And let's go to the examples here. Sorry, the exercises. Experimental version of Eliza. Try to characterize the difference of where it performs well or where it fails. Which fails, fixers, rule set. Okay. All right. All right. So, a couple of things. There is a more advanced version of Eliza already checked in that we haven't actually looked at. It's a much larger implementation of it. If we end up, in fact, you know what? Might be better to restart my REPL here. Okay. And then do a quick load. And if we do this, and let's load Eliza. Excellent. Okay. So this is the larger version of it, and it looks like in this version he corrected something that I was thinking about how to correct. That is the being able to use normal English instead of the list, but we shall see. What? Eliza's not defined. One second. For some reason, this stupid thing didn't recognize it. Let's do this. Okay. Let's see what it complains about. Oh, okay, got it. Let me just do this. Change package. Oh, sorry. That's right. Sylvester doesn't have that. No, to do that quick thing. Set package is what I need. Go to PAIP. Good. Now, if I run this, this should be available. There we go. Now, if I do hello, let's see. Yeah. So he corrected some of this stuff, and this is something that I was thinking that you could do too as well. Um, so the first thing to note is this is more of a natural version of how you would end up leveraging Eliza. All right. Read line no punctuation, as the name indicates, is because this way you don't need to deal with all the punctual. It will remove all the punctuation, and but also read from string is this is actually a common Lisp function that I don't know if we've covered here on this channel, but I will go ahead and show you what it is. It's basically read only deals with S expressions. Okay, if you use read as it is, it expects you to give it a an expression where the starting character is an open paren and the ending character is a closed paren. Read from string, if I converts that. So let me try and give you, before we continue, a different example here. I'm going to show you what this boot is. As you can see here, this is just a standard compiled function that's available to you. You could do read from string, say, oh, right. I have to also provide the actual string, hello there. And it actually figures out what it is to read in. Um, and let's do this. That's right. So what we have to do is we need to first grab a line from here. Let's do that and say hello there. And it can grab the actual string and then read from it. The one thing that you would notice though is to make things easier for us, okay, um, to make that into a proper S expression so the rest of the code specifically doesn't need to change. You end up calling this, converting it into essentially an S expression, as you can see by line 15, and then it will um, return what was actually written. So if I say hello there, oops, sorry, hello there, you can see that it will actually go in and construct the actual S expression for you. Um, and in this case, it's not an S expression; it's a list of atoms. Um, and then we can go. We've kind of covered a lot of this before in terms of reader macros that we would end up leveraging, or the use of format has here that's going through the list with spaces. Um, the main thing here is I want to show you is the number of canned responses can just grow up can grow to whatever you want in your liking, and it this particularly encapsulates a very interesting um, particularly interesting interaction that you could set with different conversations. Like for example, if I actually run this again, go back to Eliza. Where are you, Eliza? There you are. Hello there. Please state your problem. Let's say, Eliza, I remember yesterday or something like that. You could see the kind of responses that you could get. What is the connection between me and yesterday? You could see some of these questions is kind of weird because why are you trying to why is Eliza trying to um ask me about the connection between her and yesterday. Instead, a normal human being, if you heard this, you would either ask like, "What do you remember of yesterday?" or "What else do you remember?" As you see, has a canned response, um, or "Why are you recalling yesterday now?" You know, those are the kinds of responses someone else in a conversation would pick. But since this is based on a set of canned responses, it's going to give you some of these weird kind of like um, uh, grammatically correct sentences, but they make absolutely no sense in terms of the point of the conversation, which I thought was pretty funny. You can have a lot of fun with this, honestly. Um, I'm just saying, like we could you could have a lot of interesting fun with it. Um, Now in this particular exchange, like you could see that um, the kinds of questions and or answers, like like if I said, for example, to give you the sorry example, sorry about your cat, you know, just to say like he doesn't have it. Apologies are not necessary, right? But if I say it again, oops, sorry. I just ended up doing something really dumb. What did I do? That is not what I need. Hold on one second. Um, or if I ask questions like, you can see there are limitations in this card. Like if I ask questions like, I, Eliza, I before E, except after C. If I say that, it'll say please continue. It's just like you can have these like weird, like just funny conversations with it where it makes no sense as to it is, but it's just, like it 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 doesn't know how to react, and it's because of the ability of the number of canned responses that it has to detect what it is. Um, Let me do something here. One second. Um, Good. And let's see. Um, so some of this stuff can be dealt with changes to the actual rules. And we'll see an example of this when we do the next exercise with creating like stereotypical responses for like a doctor-patient relationship. This one, that next exercise is particularly interesting because the fact that uh, it's a lot of the questions and answers that people will have for their doctors, or if you like the set of writing rules for something other than English, um, are particularly hard is because context is absolutely important for giving the appropriate responses. And unfortunately, as you can clearly tell by this implementation of Eliza and its approach to actually answering questions, context is completely lost. Like we are using diagrammatic structure to create this kind of like trick into creating grammatically correct sentences, which can perfectly work. Unfortunately, without context, conversations don't make much sense, and that context and lack of understanding could result in the case of like a doctor-patient type system for Eliza, um, a situation where the patient provided enough context to actually get a diagnosis and or advice, yet because of the structure of the way they said it, or worse, because Eliza's rules had only a limited set of responses, their advice don't doesn't necessarily match what a doctor would actually provide in terms of diagnostic and or information. So um, in this particular case, though, um, changing the rule set um, is you can add new rules certainly, but I don't like for certain types of things. I'm not entirely sure if correcting the rule set would actually be necessary. Um, like you can expand the rules certainly because a lot of these basic examples do make sense. Um, One certainly things that I could certainly say is Eliza. at least at some of the older systems with that had Eliza, bye actually meant that you can exit the program. So one thing that we could do is actually uh, provide a way to abort the program instead of doing something like this where we actually return to the REPL. Um, that's something we could certainly add to this, which I think would be pretty useful. Let's see here. Let's try. Oh, sorry. Let's try. Okay. Okay. Let's do by. And the response ought to be something like, okay, then, so this is the new set of rules that we're going to use for Eliza. And um, this is only going to have it say goodbye to us in various shapes and forms. So if we run Eliza now, we say hello, state your problem. If we say bye, it'll say goodbye, but it doesn't actually exit the program. We still have the same problem that we had before. We can fix that by um, in okay, where is Eliza? Go. Okay, so he actually added a goodbye return in here, but he didn't actually provide a rule for it. So we need to add the rule. So instead of goodbye question mark, if I actually wrote goodbye in goodbye like that, I actually did this. Now I fixed this to saying this and bye like that. I rewrote it. Oops. Hello. Bye. And now, yeah, it returned A is unbound, which is because I wrote a typo when I did this. If I did this, hello, bye, goodbye. And we fixed like the issue with this with that particular thing. Um so there's a problem here. We mentioned that our version of Eliza cannot handle commas or double quotes in the input. However, it seems to handle the apostrophe in both the inputs and parens. So here, in this case, the reason, let's see, let's go and look at that example. Let's try an example here. Do this and say hello. Where is Dan's wallet? Let's see what happens. Oh, when I do that, you feel strong about. So this is coming from which um, so this is a catch-all. Okay, so here, let's see what happens when we do pattern match. Let's see. Oh, I'm gonna have to write this because the REPL won't give me this answer correctly. Go up here, do this here. Let's say pattern print pat match star s is a oh, let's say contains O, and the sentence is um, apostrophes and parens. Um, Dan's car contains a stereo. Let's see what happens with this one. And Dan's car. Okay. So let's see if I say you can't use commas. Okay. Let's say let's instead of contains, let's say are going here. We're playing around with the pattern matching here for those who are just joining in. To see why apostrophes and parentheses for the input. Like apostrophes, I have a kind of a notion. I have an understanding of this. This is basically um, uh, apostrophe. Apostrophe is basically quote in um, the uh, in the common Lisp reader, right? So it can be handled as like a no op in general. Like if you end up writing, say here, oops, sorry, if you just do that, you end up say it ends up reading and has its own reader associated with it. Okay, so this alone here is ignore um, the apostrophe. So if I do that, you could see that this becomes a double quote an apostrophe s because it this starts and tells the Lisp reader that for every character that's connected um, to this quote, until you hit a space, is part of what we call the atom. So this apostrophe s here is going to be treated that way. And we actually see this in the case of Dan's car. And because what happened is when this actually came through, Dan's car actually was read in by the Lisp reader. Dan became one atom, apostrophe s became another atom, and car became another atom. and so they didn't actually get concatenated the way you expected it to. But this is expected because apostrophe, the quote character is a special, it has special meaning to the Lisp reader. Now, in the case of comma, though, this is something I don't know. Let's say that we use Dan, George, and John are going to the theater. Okay, now here, and let's add a period there just to make things even more interesting. When I run this, you see the compilation failed. Why? Because um, comma is not inside of a back quote. Comma also is a special character in um, uh, the common Lisp reader, and it represents um, uh, the start of an unquoting operation. Okay, just like apostrophe is a quote operation, comma is an unquote operation. Okay, um, uh, so we can't. These are all kind of like special characters inside of the common Lisp reader that you have to be aware of. Um, so like if you did this, for example, I think this will probably work. I don't know. Let's see. No, it doesn't. So we need to do, um, I'm wondering if there's a way to like say, um, let me see what happens when I do this here. Oh no, I can't even do that here because of the fact that that's also has a special character. Let's do print quote comma like that. And even that also has a problem. If I do back quote comma like that, that also has an issue because it's an unquote it's expecting to unquote something. So you just can't use commas unless you wrote it into like a string. Um, so just be aware of that. Um, um, let's see what else is there. Modify to have an explicit exit. Also arrange so that the output is not parentheses either. Okay. So one of the things that I like about this book is because they're providing references with other exercises. Like there is one here about Patrick Winston Horn has a book on Lisp that contains a good pattern matching program, and to compare and contrast with the pattern matching that we have in here. Unfortunately, I don't have that book on hand, so I can't actually answer that question. Um, let's see. Oh, so maybe let me see what happens when I do um, read from string Dan, George, and John are going to the theater. So this will work if I'm not mistaken. Yeah, this will work because it's in a string. So if we do this and we print it out, we'll see that this is a string, right? But it didn't actually print out the full thing. Optional end of the start 0 and the preserve white space is probably what I need to turn on here. Okay, let's do that. Two optional arguments are provided. Okay, hold on. Start 0 and let's say 10. Just for the sake of example, let's run it. We still got a problem. Start has a problem error. Two optional must be provided before. Oh. Oh, these error optionals, is what I need to provide. Let's do this. Optional T EOF value is nil. Let's see what happens there. This compiled, but it didn't actually grab it. Interesting. Okay. We need to go and work through this a little bit. What is the comma issue? So for folks who are curious, we're trying to change the input mechanism to handle commas and other punctuation. Um, One thing here is this is partially there by just substituting like things. So like if you use read line no punct the way Norvig wrote it, this kind of works. Dang it, I cannot do this. Let me see. You could do that. You could say Dan, George, and John are going to the theater, and you can see that it's one second. Do that, and change this to that, and you can see that it splits. It basically gets rid of the punctuation altogether, and then it just converts it into a space, and then that's one way of handling it. But you lose some context with the structure by taking out some of the punctuation, provided that it provides some context, like completion of a sentence, or if the way to structure the sentence without having like say the punctuation indicating that it's a question mark or whatever, um, you might lose the sense of doubt that sometimes occurs when people are creating a statement, but um, they're not quite sure of the statement, so they use an inflection that is usually provided with a question mark. So these kinds of things are available, but if you want to alter the input, this is certainly one way of handling it. Um, what else? So a couple of these rules Um, a couple of these questions I have to actually think about a little bit more. So like adding a memory mechanism and so forth. The other thing that we could do for this is using named read tables. I forgot. We can also use named read. We could use a reader macro for this. This alternating punctuation thing. Um, I should warn folks that when we do changing of the read table, and we are going to be actually dealing with this in other chapters a little bit more. Um, you want to isolate your changes so that it is within the context of a particular function. Otherwise, you'll hit the situation where um, you cannot get out of your Lisp REPL. You have to restart it. The only way to actually get out of your Lisp REPL is to terminate the program because you altered the read table in such a way that it doesn't understand Lisp anymore. One way to work around this is, and we have seen this before, is with our example in Cypher where we ended up using named read table to define each of the individual rules, and then we can leverage that to actually go in and construct this. But um, yeah, let's go ahead and try that. In order for us to do that, I'm going to have to change this. Let me do that. And let us do a quick load of named read tables. So now this is loaded. Let us use, okay. I have to go back to our my notes on named read tables. Let's do this. Um, okay. Okay, so our named read table would require us to first create our read table. Right. So let us do that. So we need to first define our read table using named read tables colon def read table. Okay. And in def read table, we're just going to name this guy, let's say, um, let's call it Eliza syntax, I guess. we're going to merge the standard read table into this. Okay. Now we need to define our characters. We have to define our overrides. And this is where it's going to get interesting. Because what we want to do is we want it to be able to do both. Let's try. How would I do this? Because fundamentally, it's not that necessarily difficult. The main thing is, got it. Let's see if I could just do this. I'm going to write a simple function called parse input or parse string input. I'm just going to call it parse string input or read string input, because what we want to do is I'm just going to call it get next line. Okay. And all this is doing is it's going to say loop for item equals read car. And for the time being, we're just going to do standard out. I just do standard in. Sorry, not standard out. Let's see if I could just do collecting item, something like this. Okay, let's try it out. Get next line. This is a test. It will not give oh, I forgot to add the ending. This will keep on working. So I have to put until character equal item new line. It's that. Okay. Let's try that. Okay. This is a test. Boom. Okay. Right. So we need to. This is kind of the starter. Obviously, this isn't going to fly because of the fact that we need to actually also split this into correct words. We need to essentially construct what we did before with some of our earlier stuff with Neo4j, and that is we need to be able to grab each of the words individually and then throw this up, and then we can work through it. But this is kind of the starters of this kind of construction. Are there questions? Okay, if there are no questions, I'm going to end today's discussion. Um, and I'm going to spend some time actually writing out this reader macro thing a little bit more. Uh, Folks keep on pinging me. Um, and I mean, we'll be around for another, I'm going to just keep working through this example. And hopefully we'll get something kind of working the way we were expecting in the next few minutes. Again, this is open discussion, open questions. We're just going to keep going until we have at least this kind of basic infrastructure in place. Okay, so let's see here now. Um, um, let's see. Let's try this. Okay. Instead of doing the loop read car, um, let us do. We need to parse each character, construct a word. Let's see here. How did I do this last time? This was. We can ignore stream. We can ignore. We can also do. Let us do this. We do read car, but read car is going to. Um, we need to grab until space. Let me see if I can actually correct this a little bit more. No, read character is the only one that I can probably do. Or let me see if I could do read line. End of error, end of value. Um, we do this. If we do read line is going to convert into a string, which we saw before. You can see that it already did that. We just want the list of words. We need to parse the words. Um, Another way of parsing the words is use substitution concatenates from read line. But if I'm doing this with a read table, you should be able to do this the same way. Okay, hold on a second. Because read line is read tables. What he's doing before is the same. What we need to do is we need to start writing all the read functions. So we need to do def fun read space stream car. Let's declare ignore stream for now because we don't really need to deal with the stream. Just return the character. Oh, sorry. Okay. This one I think I'm pretty sure about. Yeah, I'm gonna have to do some of these other stuff. There's a little boilerplate that I'm gonna have to do in order for me to actually construct this because, and hold on, let me just go ahead and do this case preserve. There we go. Now we can write our overrides, and our overrides are going to have macro character associated with the callback. So macro car. Here, space is going to just be space. And we do read car, sorry, read space. Right. Now the question is should this be part of read line or not? But yeah, this is going to require me to go look into how to convert, how to effectively implement something without overriding readline. Because readline already does some of the stuff that we saw earlier with read car. We just need to convert it so that it can take in um, a non-Lisp syntax and convert it into a Lisp syntax without doing what the hack that we saw earlier. Um, okay, I think there's another way of doing this, which is let's try this again with this get next line that we wrote earlier. And then let's do loop for item equals read car, read car until let's see if we do this and then we do for um I don't know if this is going to work, but this is going to be very imperative in terms of its syntax. We'll see if this will work or not. Car equal okay. Um, do if ah I think this might work. We'll see. When car equals space, we've already parsed everything up until that point. Collect word else. Set f word to being the concatenation of what we currently created with word and the next item. Let me see if I could also initialize this to an empty string for the time being. This is I don't know if this is... Okay, I already kind of... If one error. What is the error? Hold on. Oh, it's not liking um okay. Let me see if I can do this. I don't know if this is gonna work correct that, but we will see when ah, okay. So it's not liking the fact that I'm trying to do a lot of work in the mini language and it trying to do a do. All right. Okay. Looks like we're going to actually have to create our own collection. Fine. I could do that. I'll figure out a way to actually clean this up, but there is one way of probably handling this, which is let me just see one thing. Concatenate. This will not work. Right. So what we're gonna have to do is do this instead. Do sorry this format nil a a oh, forgot. That's what I need to do. Which means this may have worked also. No, because of the fact that this. Okay, so do this. Do progn unless car equal item space okay set a forward to being concatenate string word format nil tilde a item. Okay. What did I just do? Hold on. I have to rewrite this because I pasted something that I should not have pasted. There we go. Okay. Okay. So this is going to construct a word. And then we need to push it onto a list. So let's go ahead and create that list, shall we? Um, create an empty list. So now, oh, right, we can't do it that way, can we? We're going to have to do if. Fine. If it equals a space, then we just need to push new object, which is our word, into our resulting list, and then we need to empty out that list. So we need to do another prog n here. Create a new block. Then we need to go in for do that. Start it over again. So now this should work the way I think it should, but we will see. Get next line. This is a test. Let's see what happens. Ooh, forgot to actually return. As I expected. There we go. Res. Now this may not be reversed because I may have to reverse this. Oh, it did not. Okay. Give me a second. That means the set word did not actually work the way I expected it to. Let's try a simple example. This is nil because it did not actually push the last item into the list. Let me do one thing. Let's see if I could do this in. Um, okay, this is going to take a little bit of time. I'm going to have to figure out what exactly this is going to do, and we're over time today. So tune in next week where I actually hopefully will have a read table by then that I can actually cover a little bit more detail. Um, but I have to play around with some of this stuff a little bit more. Thank you guys for joining. I appreciate the continuing onlookers. Please subscribe. Hit the bell icon before you leave. If you guys have any questions, comments, topics, please post them in the comments by all means, and I will address them accordingly. Um, we should have an episode at some point to actually also cover all these too as well, all the comments that have been coming up. And I hope to see you guys next week. One announcement before I let you guys go. Next week, we're probably going to be starting a little later than normal. Our usual time is at 1 to 3 p.m. Next week is probably going to be another evening session from 5 to 7. Thank you all for joining. Thanks.